Am I audible, first of all? A reaction? No. Good. Uh, yeah, I hope I'm audible clearly. So I hope you enjoyed the previous sessions, and I hope you'll enjoy this one too. Uh, to start off, I'm Srijan, and I'm someone who's very interested in like the interdisciplinary field of like machine learning in natural sciences. Uh, and yeah, today's topic is on physics-inspired computation. Uh, yeah, I'll start presenting now. Is the screen visible? Yeah. So to start off this session, I would like to share this quote. Uh, every problem has a solution. It may sometimes just need another perspective. So this is something like when I read this quote, I felt, oh yeah, this is very true. Like there are a lot of problems that you may face, not just in academics or some particular problem, but anywhere there might be a solution somewhere else. And this is the kind of thing that we'll be looking at today. And first of all, I would like to start off with the completely unrelated, but somewhat related to this thing here. So invention of Velcro. So you may think invention of Velcro, what does that have to do with physics inspired computation? So I just want to show that some problems can be solved using inspired from something else. So this guy, George de Mestral, he went on a hunting trip in 1940s. And while returning back from that hunting trip, he saw that his socks, his coat, and also the fur of his dog, they were all covered with something, a burdock seeds. And that made him think, can I design something that sticks just like how this burdock seeds stick? And that is how Velcros were born. And now Velcros are everywhere, as you might know. So now let's go to nature inspired computing. Like how has nature inspired in a particular field, that is computing? So there are mainly three types of how nature has inspired computing. One is how has nature inspired to develop novel problem solving techniques that we'll be discussing much more in detail today. Use of computer to synthesize natural phenomena is basically simulations and everything. And employing natural materials to compute, which is like, as you might know, quantum computers, the one on the screen right here. So quantum computers are something that is inspired from physics, which use uh, qubits instead of the normal bits to compute. All this is fine, but there is something that has inspired computing in a very, very big way in the recent past few years. Uh, can anyone guess what it is? Just write it in the chat box. Any guesses? What could be something that has inspired a lot of people? I mean, not uh, a lot of problems were solved, and like I think it has changed the way we look at internet. Anyone can't think of anything, bro? Okay, then I'll tell. what it is. So all of you guys might have heard of ChatGPT, right? Yeah. So ChatGPTs are usually based on neural networks and not neural networks exactly. They are something called transformers, but this neural networks, they're inspired from how human brains work. So I think most of us have used ChatGPT to a very good extent. But again, this is something that has been inspired from nature, and I think yeah, every one of us should appreciate how nature helps to find out new ways to solve problems. Now let's go to how has physics inspired. Like all this stuff, yeah, I have put a what lot of ants in this picture. Can any one of you guess why? Why have I put so a picture of so many ants there? You can write it in the chat box. I can see raised hands. So basically, even ants have
Hello.
in hello, yeah,
Yeah, the ants, I mean, they said they have some chemicals which help them to find the roots when they help in forming the networks. So, kind of inspired from that.
yeah. So basically, ants have something. I mean, there is something called as ant colony optimization, which is also an inspired algorithm. And yeah, a lot of the stuff you see are inspired from either biological or physical processes. And that is what uh, why like this is one of them. Yeah. Let's go to- yeah. So physics inspired computing. We'll talk about a few more algorithms and everything that is inspired from physics as we move along the lecture. But firstly, yeah, what is it? So what it basically is that there are some principles in physics which are used to develop an algorithm that will be used to solve some problems in some other domains. So yeah, it can these approaches sometimes are better than the normal methods that are used to solve problems. So where do you think these methods are applied? Like usually, what do you think? How do you think these methods have in helped humans solve problems? So basically, I'll be covering a particular set of algorithms called optimization problems. So I'll be mostly dealing with optimization of various stuff. So optimization problems are everywhere. Even machine learning is an optimization problem. Or be it, I think all of you guys have done linear programming in your schools, which is again a optimization problem. But there are also more optimization problems like optimal power flow problems or energy managements, clustering, electronic circuit designs, antenna designs, etc. So all these problems, they are kind of solved uh, using physics inspired algorithms as well as normal algorithms as well. So before jumping into all those algorithms, I would just like to uh, go a little bit into what is optimization. So optimization, as the name suggests, is finding the optimum of something. It might be the maximum, it might be the minimum, but it is to find the optimum case. Say for uh, uh, what example do I give? Yeah, for a runner, for example, he has to optimize his speed, like to get the maximum speed. While for a long distance runner, he might have to optimize his speed as well as his energy because people are not able to type in chat. Why is that so? Just give me a second. Are you guys able to type in chat now? Just give me a second. Is that something to do with the channel settings? Think so. Yeah. Vedansh, are you? Oh, okay, yeah. I think it is fine now, right? People are able to type. I can see that. Yeah, cool. Yeah, sorry for that. So where was I? Yeah, I was explaining optimization. So yeah, like I said, for a short distance runner, it might be time and speed that he has to optimize. While for a long distance runner, he has to also take into account energy, like he has to conserve energy properly so that he covers the entire distance. So this optimization as such differs from case to case basis. It's not the same for each and every single thing. And before I jump into uh, what is optimization, more stuff, I'll just give a little bit of vocabulary and of the optimization problem. Let me just share the screen of. So is the screen visible? I don't think so. Wait a minute. Yeah, I assume screen is visible now. So some of the stuff in optimization problems that just you need to know we have something called as the objective function. So you usually denote it by fx, and this is the objective function. So my handwriting is legible, I suppose. So what is the objective function? The objective function is the function that you are trying to minimize or maximize. Basically, the function that uh, you will optimize, and you will have various variables. Let's name them x1, uh, x1, x2, x3, x4, and so on. So what are these? These are the variables, and you have complete control over them. So you can change your these are your parameters, which you can like change as per as you want. And then you will also have constraints. So constraints, for example, it could be like x1 uh, plus x2 should be less than some number, say 100. This is just a linear constraint, but it could be anything. It could be a quadratic constraint, or it could be anything. So many of you guys might have done the linear programming this thing. So a LP program, as you might know, you will have z is equal to some f of x comma y, and then you will. So this is your objective function, which you try to uh, maximize or minimize depending on what you need. And then you will also have something like uh, x plus 3y should be less than 10. And you will have something like y plus, let's say y minus x is greater than 5. And then what you used to do is, I hope everyone knows this thing where you used to draw some graphs. So it will be something like this. And you'll also have some constraints like x greater than 0, y greater than 0 or something. And you consider the feasible region like this. And then you consider the extremities. So optimization problems are again, they are similar to this, but in they can span n dimensions. So yeah, imagining something in n dimensions is not very feasible. Like you might not think of uh, having, yeah, these are LPPs, but uh, there are several other this thing. Yeah, I see a question in the chat box. What does minimizing and maximizing exactly mean? Uh, Say you have something like fx is equal to 1 minus 2x square. So now what is the minimum value this function can attain in all space? So x can be anywhere. X belongs to the set of real numbers. What is the minimum value this function can achieve? But this function might be dependent on many other things. That is what this thing is. So no, here I think it's the maximum value, but yeah. Uh, so in LPPs, you do this. In basic optimization problems, again, you'll have some space based on some constraints and everything. And in that space, you're supposed to find the best space, the best solution. So other simple example is y is equal to x square, where you know that this is the minimum. So these are what basically optimization problems are. And now let's go to some different types of optimization problems. So there are continuous versus discrete optimization problems. So what are continuous optimization problems? They are basically optimization problems where the space is continuous. So search space, which is basically where all your solutions can lie, the feasible region. Uh, Sometimes it might be R also in some cases, but wherever it is continuous, it is not like based on like only certain integer values it can take or something like that, then it is continuous. Discrete is when it can take integer values as well. Constrained versus unconstrained is also one more thing. So uh, constrained versus unconstrained. So basically, constrained means you're constrained, putting some constraints on your search space, while unconstrained is on whole space. That is saying x comma, if it is a two-dimensional space, you are searching the whole of two-dimensional space. Uh, that is what constrained versus unconstrained is. One more this thing, classes of optimization is deterministic versus stochastic. So what is this deterministic versus stochastic? So a deterministic process is something that will happen according to a given set of rules. So there is no ambiguity or there is no probability. A stochastic process, on the other hand, will be something that has some probability. So say something like, okay, tomorrow is a Sunday. That is deterministic, like you know for sure. But saying something like tomorrow it may rain, it's a probability. So even in optimization problems, there are some stuff which are like deterministic. So you start at particular points and go on and stuff like that. And then there are also probabilistic. So you start and you take certain steps according to certain probabilities, which are again randomly generated and stuff like that. So that is deterministic versus stochastic. Uh, so shift to wait. So there are also certain other optimization techniques like gradient based techniques are there. So uh, have you guys heard of the gradient descent? Yeah. So that is also a optimization technique. You have something like this and you take the gradients here and then decide where which direction you go to and then attain the minimas and as such. And then there are like certain algorithms. So there is something called as exact algorithms. So any idea what are exact algorithms? No. Anyone else? So without any conditions is not exactly branch income. Yeah. Yeah, it's obviously a method to solve problem, but what do you think exact? Focus on the word exact. I think you'll be able to spell it out better. Okay. So say something like uh, you have this, and you certainly know that this is the minimum, and you can exactly reach the uh, minimum of this particular function. But when uh, your objective function gets very complicated, no, it's not to solve with the same set of constraints. Okay, I'll tell what, yeah, I'm explaining that right now. So you have a very complex n-dimensional space, which is like, say, uh, let's say around 100 dimensions or something. And you have to, uh, yeah, you're on the right track. So it will have one global minima, and algorithms which get the global minima, they are what exact algorithms are. So they search the entire space and get the global minima. But getting the global minima when you have a lot of dimensions is not really computationally reasonable. It will take a lot of compute power and a lot of time, which is why we shift to something called as heuristic algorithms. So what do you guys think heuristic algorithms are? Linear regression is not exact algorithm, since it does converge, but no, once you attain the minima, yeah, it is like it does not change anymore. So you can maybe say it's an exact, but again, if linear regression doesn't always give you the uh, best uh, linear regression doesn't always give you the global minima. I mean, yeah, they sometimes might give you local minima as well. That's the thing. So similar to the right, yeah, yeah, heuristics. That's what it is. So they are algorithms which are more quick, less computationally expensive, but then again, they might not be finding you the most optimal solution. They'll find something that is right. Don't understand linear. Okay, I don't understand linear can be used anywhere. I don't understand like what do you mean by that? not all uh, functions are like based on linearity. Like there are logistic or exponential relations as such. So yeah, exact algorithm means that an algorithm that can get us the exact answer. So that is what exact algorithms are. Heuristic, on the other hand, are something that optimizes, but not to the you are not sure if it's the global minima, like if it's the most optimal solution. It will give you something that is optimal. So those are heuristic solutions. So this heuristic here, it means to know in Greek. So yeah, not following Q&A part, I'll just disable that. Yeah, that is what heuristic is. It might not, it gives us an approximate solution which is good enough to work with. It's not exactly like uh, uh, exact algorithm. So again, exact algorithm will more so you can think of it this way, I suppose, like uh, you, yeah, heuristic is quick, but it may not be optimal. That's true. Uh, yes, we work with the heuristic algorithms whenever we cannot use an exact algorithm. Exact algorithms are not always feasible. So that is the main thing. Uh, so heuristic algorithms, they mean to know in Greek. Like that is what heuristic means. Uh, so yeah, they provide a good this thing, and these heuristic algorithms are usually inspired from physical or biological processes. Say, yeah, I talked about ant colony optimization. There is something called as swarm optimization and particle swarm optimization, PSO. And then we are going to talk about, today we are going to talk about two algorithms, uh, central force optimization and gravitational search algorithm. So these two are again heuristic algorithms that I used. They have been used in various domains and have shown to give good result. Yeah, the last this thing, I think I told that we work with heuristic algorithms whenever we cannot use an exact algorithm. Like when it is computationally too expensive, we just go with heuristic ones. I hope that is clear. Okay. Uh, so these right here, usually heuristic processes are stochastic processes, and also they are population based. but this is a deterministic algorithm. So both these algorithms, they are based on Newton's law of gravitation. I hope everyone knows what Newton's law of gravitation is. Okay. So what is population-based algorithms? Stochastic deterministic, I have already told about. Population-based as in, so say in a n-dimensional space. Okay, I've been using a lot of n-dimensional space. Think it as three-dimensional space. So in three-dimensional space, you start off at in a normal, say something like a linear regression. You start off at a point and converge to the minimum. But in population-based algorithms, what you do is you start off at multiple points, and based off that, you converge based on how everyone else is performing. So you have a population, you have like say m agents, and they get information from each other. So this is what usually uh, population-based algorithms are. Now I'll formulate what gravitational search algorithm is. Both central force optimization and gravitational search algorithm are pretty much this same thing with some differences in. Oh, okay. Uh, Say it's a 2D space. I'm just drawing like a plane here, but consider like it has its own bumps and uh, valleys. So there are something like there are so it's a 3D like a 3D plane where there are bumps and everything. Uh, so in a just like a linear regression or something like that, you start off at one point, say the minima is here, you just converge to this point. But if you are uh, but on a in a population based algorithm, you start off like so these, let me use a different color for the, so all these your red circles, whatever, so they are your agents. Oh, I'll tell you how it is stochastic. I'll tell it's in the formulation how it's stochastic. Uh, so basically you have these many agents and you assign something called as fitness function. So each and every uh, this thing decides based on the fitness function of the collective. You decide where to go. So where the global minima might exist. It might not always be global minima, but yeah, where the most minimum of the minimas. So instead of having just okay, let me explain it in a thing. So you have something like this. Okay. So say you start off here with a single particle. Now using something called like linear regression, you'll just directly end up here, which is again not a global minima. It's a local minima, as you guys can see. But if you have something like 3, 4 particles, so Now, based on all these information, you can like, so this will say, okay, I have found lesser optimization that is better than what you have found. Something like that. So that is what you have multiple starting points, and also there is information transfer. You somehow say like based on various formulate it such that you have some sort of information transfer. I'll tell how that happens for gravitational search algorithm. Is that clear what population based? Uh, there is not exactly a need. Sometimes you don't really need the global minima, but it's not necessarily global minima also. It can be maxima or minima, whatever. So why global optima say anything? Optimizing as much as you possibly can is better than having something that is like not really that good. Say, for example, you want to optimize how you uh, go around the city. So obviously you will have to like, you have your car, you want to go around the city. You won't obviously go to the uh, something that is in one corner and then goes to somewhere else that is in the next corner, and then go somewhere in the middle or something like that. You would obviously follow some path that is, saves you fuel, saves you money, etc. So, which is, and again, global minima in these kind of cases is not really that necessary. You can work with something that is better than the random case. That is what I just wanted to. I hope that is clear. So, yeah, gravitational search algorithm. Uh, Newton's law of gravitation, which is Gm1 m2 by r square. I hope everyone knows this. So also, you know that force is equal to mass by acceleration. So one thing, yeah, this is two particles. I think there is some sort of delay between me writing here and fine. Uh, yeah. One thing about these in gravitational search algorithm, or even actually this thing. So you know that you think this gravitational constant is a constant, but G depends on time. So it depends on time as this. So beta is a very small number, which is to be determined based on various data. Um, so this is the time it has been since universe was born, and this is the current time. I mean, this is the time at which universe was born, and this is the current time. Yeah, T naught. Right. So this is kind of what makes. Also, there are some other stuff that makes it fantastic. Uh, yeah, and you have there is active gravitational mass. and there is passive, and there is also inertial mass. So no, this is not. I mean, the gravitational constant. That is, I'm not exactly sure. Like that is a paper in itself that I haven't gone through completely. So uh, they have proposed that there is the gravitational constant isn't uh, same at all points in time. This algorithm isn't based on Big Bang. So what are this passive, active, and inertial mass? So active gravitational mass is strength of gravitational field. Yeah, so this is just something that is assumed, like we have taken this for the sake of the algorithm so that okay, yeah, something that I haven't explained here. So that is common in population-based algorithms. Mm, there is something called as exploration and exploitation. So what do you think exploration and exploitation mean? Or why we usually use this? I'll actually start off by giving an example here. So you have many restaurants in your city. You'll have a lot of them. So what you do is, yeah, it's explore something. So you have, say, 100 restaurants in your city. You visit a few of them based on like reviews or something. You visit them. You visit a lot of restaurants, and that is your exploration. What is exploitation? You find that some restaurant serves really good food, and now you go to that restaurant continuously and try different items on their menu. So this is, yeah, uh, that basically is it. So basically, you know that that particular restaurant is good. So what you do is you go there continuously and try different items in their menu. But also sometimes you feel like exploring and going to different restaurants as well. So this is the basic idea behind exploration and exploitation. So why this is done is to avoid local minimas. So you don't want a local minima which is like, so you have something like this. You don't want to be stuck here, which is why uh, you have exploration and exploitation. Say you got something like this, then you would obviously uh, you'll again explore. If you get something like this is probably fine, which is what to avoid global minima, local minimas, you do this exploration and exploitation. Yeah, it helps if in finding more optimal points. Okay, so I hope that is clear. Yeah. So coming back to active mass is strength of gravitational field, and passive mass is strength of how it interacts with the graph. Yeah. Uh, Exploitation is okay. You know that a particular area is good enough. So consider this is a three-dimensional space. There is one more dimension into the plane. So you know that around this area, yeah, when you use that particular location more often, so around this space, you can go more often and find more points that are optimal. That is exploitation. Is that clear? Okay. So yeah, passive mass is how it interacts, like strength of interaction. And I hope everyone knows what is inertial mass. What is inertial mass? It's okay. It's just the resistance to change in state of motion, which you have learned in, I think, ninth grade. It was resistance to uh, uh, gravitational search algorithm uses all the linear regression. Uh, I mean, it might have a lot more in one dimension. I mean, two dimensions, yes, but if you have more and more this thing, it will be, yeah, in more complex cases, you need to do both exploration and exploitation. Okay, so GSA, one thing, so GSA is basically gravitational search algorithm. I'll be telling it as GSA now. So they have taken one thing, that is they have considered the force to be inversely proportional to 1 by r instead of the usual 1 by r square. This is just a convention that the algorithm was formulated as. So now, how is the algorithm in itself? Say you have m agents, uh, and each one you initialize with certain positions. Say you have xi. So this is your ith agent, and the position will be like xi1. So the 1, 2, 3 here represents the dimension in which that position is, and so on, and you have n dimensions here. So this is what, and I also will be from 1 to m, because there are m agents. And now you define the force in one particular direction. So what you do is you use g of t into m. So this is force between I and j at time t. So you have active mass of j, and then you divide it by the distance between the two particles and as well as at that particular time, and you add an epsilon. So why do you think this epsilon is added? Anyone? And then also multiply by the distance in that particular. So this is how right, uh, this is how the force and GSA is. So basically, it was found experimentally, like doing a lot of computations, that inverse of R provided better results than inverse of R square. And that is the reason why R was used. Uh, and epsilon is, no, epsilon, okay. Epsilon is used because of the reason that you don't want the distance between them to be absolutely zero. So what will happen if uh, two particles like are in, I mean, computationally, it's very much possible, right? Although in uh, physically, it's not possible to have two objects at the same spot, but computationally, there might be possibilities. So then this will shoot up and this will become infinity if R becomes zero. To avoid such case, we are adding an epsilon. Uh, yeah. And now the total force is calculated. And now this is where the main, like the stochastic term comes in. So the total force T, I mean, in the D dimension on J gets calculated here. And what you do is you sum up while having a random integer. So you have something random multiplied by the above force. So this is where the stochastic nature of gravitational search algorithm comes in. Is that clear? Someone had asked that question, right? Okay. So now again, there are some more steps, which is you have your oh, this method just okay. I'll show you the. I have a code which I'll show in a few minutes. So it can be used for a lot of stuff. So I have used it to like optimize something called as the Ackley function, which is standard function that is used to like check the convergence of functions. So yeah, please repeat the stochastic part. Okay, so you have multiple bodies here. Uh, you have one, two, three, four, five. You have a lot of bodies. And on this particular agent or body, whatever. So forces from all these are acting. If you just have it, if you have it multiplied by one, it will be a deterministic process pretty much. But to have some kind of stochasticity, what we are doing is we are multiplying it by some each and every force by some random integer. So it will be say some 0.5. This will be 0.1 and so on. So this is why, so the probability is a uniform distribution between 0 and 1, like random integer. So yeah, I had to mention that. Random integer is between 0 and 1. It's a uniform distribution. But then again, since it's probability, the algorithm is stochastic. Is that clear? And then in the end, what you do is you have your distances. You had some initial position. Now you update that initial position with some accelerate, like you have the, let me first define how velocity is defined. So you have velocity at t plus 1, and this will be again random times velocity at t plus acceleration at t. Acceleration, how do you get that? You get that by this thing, using this thing. That will be covered in the next, like you won't get much, just the flavor of quantum computing will be covered in the next session. And then you also have x at t plus 1. These are your basic uh, laws of motion that are derived from, uh, yeah, I think you all know the v is equal to u plus at, the same thing, but these are defined a little more with some randomness and everything. And then there is also something called as fitness. So fitness is basically which is most near the this thing. Uh, uh, and based on what you want, whether you want maxima or minima, you choose what kind of fitness you want. So you either like for a minimization case, you take minimum of fitness. Fitness is basically your score. It's a score assigned to like how close it is to the optimal solution and as such. And yeah, so this is the best fitness, and worst fitness would be extent. So now also what is done is you have, I told you have M agents. So out of the M agents, we only select K agents which have the best fitness, like which are closer to the optimal cases. And that closest optimal, okay, I think I didn't really explain how exactly this works, right? Okay, so consider how this algorithm works. You have some solar bodies, uh, some bodies, and you know that gravity is always attractive and it attracts towards the one that is most heavy. So here what is being done is all the agents are attracted towards uh, agents which has the highest mass. So that is what this is about. I think I'll show it to you in code. Like I have some So I hope the code is visible. So yeah, here there is something like the Ackley function. This is called the Ackley function. I won't go into how that is defined and everything. And yeah, I have evaluated this. I'll first show the, yeah, so I don't think I can use the, so here, I hope this is clear. Uh, you can see that the particles which are near the optimal solution, they have higher mass, which is they have higher fitness. And this around here is where the optimal solution is. And you can see the ones that are very far away, they have very less mass. You can consider like them having them being smaller is them having lesser mass. So ideally, what should happen is they should converge at the point where there is optimal solution, because that is where the highest mass will be. So you can see that everything has started to come closer because the higher mass objects are pulling them in. You can see here. And as you go closer and closer, you can see that we are getting closer. I think I have a video, right? So you can see how they get closer and closer to the optimum, and then yeah, they're slowly converging here, and you can see they have converged. So what is meant by converging is that they have just attained the optimum value. So you can see that all pretty much have converged at the zero, that is the optimum value from here, which was random. Any questions regarding this? Yeah, I'll share the notes. So yeah, do I need to go through this code? I'll share the code as well. So you can see this is your best value, and uh, this is the number of iterations. And as you move forward in time, uh, you can see that the particles are attracted towards the optimal solution. Just like how in gravity, everything is attracted towards the one with the highest mass. So any questions? I'll stop for a while here for any questions. And then we shall move on to something called as physics-inspired neural networks. Uh, yeah, so masses are not something that we choose. So uh, masses are something that uh, is based on how much closer to optimal solution, like how optimal the solution is. Uh, yeah, if that is clear, what peak, what the y-axis is basically your value of the function, uh, and that is to be minimized, and that is what you could see in the graph. No, the fitting is again, it's based on this algorithm, based on gravitational search algorithm, where like you have all the, yeah, you have the, do you want me to go through the code? I'll share the notebook. Physics inspired neural networks are not quantum neural networks. They are something else. We'll go through. Uh, yeah. So I was talking about how let me share my. So I was basically talking about how neural networks are inspired from brains. So wait a minute. Why is this so? Yeah. Position are okay. The position of those masses are first initialized randomly. So at some random positions in space, they are initialized. Whatever your graph or wherever your space is there, in that space, you initialize the positions randomly. Is that clear? Okay. So now, yeah, I was talking about how neural networks are something that was uh, mostly inspired from brains. So any of you have idea what neural networks are? Okay, I'll just start off. So neural networks are something that works similar to, yeah, they're uh, inspired from human brains, human nervous system. So these things right here, they are called as nodes, or basically the neurons in uh, human brain or humans system. Uh, so these nodes are similar to this thing, and each of the node is connected to each and every other node here in a neural network. I'm not connecting everything because it will be a mess. Uh, so this is what it is. So you have a set of nodes, each connected. Yeah. Uh, so there are connections. You get some input here and you get some output here. Say for something like you touch a hot object, you get the input as heat, and the output is your action, your reflexive action. But in a neural network, your input could be, say, a picture of a dog. And neural network will predict that it is a dog. Yeah, there are input layers and hidden layers in this one. So this is basically the idea behind a simple neural network. There are various complications behind like what they are. So each node has, each connection has something called as weights uh, and biases. And there is also something called as, yeah, activation functions at each layer. Uh, these are all like simple uh, activation function just adds some function on top of the value that you have at that particular node. So you can kind of think of it as like you have uh, some data and you decide what to do with that data based on applying that after applying that filter. So yeah, it's kind of like a filter. And yeah, that is pretty much it about a neural network. But main work in a neural network happens through something called as loss function. So does anyone of you know what a loss function is? Yeah, there are different types of neural networks, but I want to focus on physics inspired ones. Why they are, yeah, they are cost function. Cost function and loss function is the same thing. So basically, for a linear regression problem, uh, you have points and you have a line. Now you have various distances. Pardon the not so straight lines and everything. So this distance right here varies. And yes, loss function should be less to obtain optimization. That is correct. So that is what you do in neural networks. You optimize the loss function such that it is the minimum. And there's something called as mean squared error, which is basically mean squared, which is you have your actual data. Uh, I mean, whatever the prediction is there, and uh, your true value squared 1 by n times. So this is the usual loss function that is used. So a loss function is your basically objective. This is your objective function, which you are supposed to minimize or maximize, depends on how you formulate this. But say you have done a physics experiment and you have obtained some certain data points. Say you had done a damped, so I'll be talking about damped harmonic oscillators. So there is a spring and you have a mass hanging. So in an ideal case, you know that it should be a oscillation which does not reduce. But in reality, it will be something like this. Right? It will be damped. So, say you did this experiment, the experiment of damped harmonic oscillator. Now, what you do is you have certain points here. Say you have point here, 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 here. And after a certain time, you weren't able to get the points. So now, when you fit a curve, it should be something like this. But you don't know what will happen after this particular point. But since you know how this equation behaves, you'll be like, okay, this should be something like this. Right. But a machine learning model, it won't know what to do. So what will it do is it will come here until here, and then it will be like, okay, fine. This is how I'll go. So this example that I'm giving right here is a very simple example. But one thing is we can fix this. So I just define the equations for how this thing is done. So the damped harmonic oscillator is defined as such. Uh, the friction, the second term is the friction term. This will what the damped harmonic oscillators will be. Where to use it? Where to use what? This physics inspired neural networks. They're used pretty much like, say you want to, yeah. So scientific machine learning is a upcoming field. Like I don't know how many of you have heard about it. So anything to say predict some natural phenomena, like I had seen it being used for seismology, which is to uh, predict earthquakes and stuff like that. So there you know the equations. So you use the like instead of normal neural networks, physics inspired ones were used. So again, coming back to what this is, I'll actually show you a very nice this thing. Just give me a second. So you can see the three uh, animations here. So this one, can you guys see this? Can you guys see this now? Yeah, okay. So we can see that the first one is a physics inspired neural network. This is an animation of damped harmonic oscillator. This is something that we already know that I'm discussing, just so that you get an idea of how these are used. These can be used to much more complex problems in physics or anything like wherever differential equations are used fitting it. And this is what, yeah, like I said, this is what a neural network will do. It will come, it will arrange itself until the points are there, and then it will be like, okay, I'm going this way. screen which I was sharing is not no longer being shared. Yeah, prediction will. This is very ideal case that we have assumed. Your actual data from your data points, it won't be very ideal. So if you have done experiments in your school and everything, you will know that uh, you will have points like something. Let me see if I have the so you will have points something like this. So when you try to connect something over here, you will have a line like this. Uh, Here, the data points were generated such that it was along the line of damped harmonic oscillator, which is why it was very easy to minimize the this thing. And besides, this is a very ideal case that we are considering, which is why prediction seems very accurate. This is also something we know, like for whoever has learned harmonic oscillators, it is something that we know is something like this. Uh, but in reality, it won't be the case. So yeah, sorry, okay. This is the equation of your the oscillator. So what you do is, in such cases, for your loss function, which is your MSC, you add a term such that it is you add this particular loss, uh, which is defined something like this. So summation for all this time and this time. So you have L, which is your loss function, which will be your mean squared error, which I have defined. So I have defined mean square error here, which is your difference between the prediction and the actual value. But to this factor, you add your physics loss, which is loss squared. So this is what you add so that you get a better uh, yeah, attendance link. I'll send that. I'll also share the QR code. Uh, yeah. So you have this. So what we are trying to do here is, I'll take the example of the very simple hum harmonic oscillator. So you have d square by x. Any just give me a second. So you have this uh, is it writing now? Yeah. So you have d square x by dt square is equal to minus omega square x. I think this is something standard that everyone will uh, everyone has seen, I suppose. Something that we write as x double dot minus plus omega square x is equal to 0. So what we do here is that we try to minimize this. So in your experimental data from the graph that we get. So in a normal neural network, you'll try only minimizing until one particular point and then go off. But here, since you try to minimize this for all space, yes, this is the simple harmonic motion, SHM. Uh, what happens is, uh, even if there is no data, it will continue to minimize its error, which includes the physics part. So basically, you are telling the network that there is some physics involved, learn the physics behind it. Because usually the neural networks are like, okay, I'm given this data, I have uh, this particular, so this is the particular output for that particular data. But the physics behind or whatever the science behind them, the neural network doesn't learn, which is why you have something, uh, yeah, you teach the physics behind it so that it accurately maps to the this thing. Again, I have some code of the same, which I'll share now. Okay, before that, any questions about like physics inspired neural networks, anything? Because I didn't really explain neural networks that well. So yeah, you can unmute now, whoever has raised the
How do
hand.
you add it to that? Like, how do you teach the physics to the network? Like,
Oh
do
yeah,
we add the?
yeah. So your loss function, which I told, this is your optimization function, right? So you have
Yes.
something called as MSE, which is uh, so you have the mean squared error, which is the error like how differing it is from your actual points. So you try to reduce your mean squared error. That will tell it to stick with the experimental data while you have this particular term. which is your equation. If you notice, this is your equation. This is your equation of harmonic oscillators, which are damped. So you're telling, while minimizing this, also try minimizing this particular function. This one. So this is how you teach the neural network to minimize, to study the physics. Yeah, the attendance will be recorded as well. So for this, I have much simpler code. So I'll just, yeah, any more question? You can either raise your hand or if nothing, I'll go on to show the code. So this is the code for uh, this physics inspired neural networks. So what I've done here is I have defined the solution first of all. So I hope this is visible, or is it not? Yeah, now it should be visible. It's visible, right? I assume this is visible. Yeah, good.
Yeah, it's visible.
Yeah, yeah, cool. Uh, okay. So, okay. So this first function, what I've done is just to generate some data points as your experimental data points. So uh, it's just getting the actual solution because you know the actual solution. This won't be the case every time. You will have to get the data from some experiments, and these are just helper functions. And now define a neural network. So okay, I don't think I'll be able to go into everything of like this is how you define a model, basically the model architecture for a neural network. So you have a fully connected layer here and one more fully connected layer here and a linear layer in the end. Yeah. So you have three layers here, which is 1, 2, 3, and then uh, yeah, it basically is a simple neural network. And yeah, this is where the you have the x, which is some random points, not random points from uh, 0 to 1, 500 points. Yeah. And then you have y, which are your experimental points uh, at these locations. And now you can see, okay, yeah. Here you can see these are the experimental points that you have generated artificially, which I have done here. So yeah, can anyone say why I've used this thing assert d is less than w naught? Okay, Torch library is used for like all sorts of machine learning programs. I think yesterday you guys used scikit-learn. I'm not sure what the last session. Yeah. So this is to avoid cases of so this goes into the physics of it. There are cases like underdamping, critical damping, and overdamping. So in the overdamping case, what happens is it never oscillates. And critical damping, it just has one oscillate. I mean, once it goes down and then it again stops oscillating. But for underdamping part, it has an oscillation that frequently that is like with time it goes down the frequency of it. So which is why we have this. So I can actually show you. Yeah, it kind of works, but it is just saying that uh, you have to always have d less than if the condition is not satisfied, it won't do anything. But assert will be like this is a required condition, please fulfill it. So yeah, and you can see this is the training data we have, and this is the exact solution. Now, so this is where training is done. So I have put it for, and let's train it for say 500 steps with 20. So did you guys in the last session use scikit-learn? I'm not sure what you guys used for the machine learning in astronomy part. Yeah, scikit-learn, right? Yeah. So scikit-learn is something that has the basic algorithms, while Torch is also something that is widely used in machine learning, more so for like very complex uh, algorithm. I mean, yeah, architectures and stuff like that. So basically, yeah, if I have that, yeah. So you can see it starts off as nothing but a straight line, and then based on it starts bending, and you can see that by 200 step, it has almost formed the this part of it. While yeah, and then after a certain point, it will not move much. It will be very much stagnant. While physics need 2000, 20,000 steps here. Fine, let's say, let's have again 500 steps with 20 SQ. So you can see how a normal neural network works here. And Uh, okay, not learning anything. Let's see something like what is that? This should work. It will take a little time to train and everything based on how fast your computer is. And yeah, this is a lot of steps. So I can actually just show you the. So this is what it is in 6,000 step. Maybe I can decrease this to 600 and show you various. Yeah, you can see it has gone from this to this. And yeah, I forgot to mention about one thing here, the green dots. You can see the green dots there. What do you think the green dots are there are for? So it's supposed to be till 11, 1, right? Yeah, I'll share the code. I'll share the code in the Teams channel itself. Yeah, so you can see this has almost become exact solution. Not almost, it has become the exact solution. I'll share this code with you guys. Yeah, I think that's it from my side. If you have any questions, you can ask. I just shared the listing, well, the QR code. Yeah. This is the QR code for the feedback slash attendance.
Hello, sir.
Yeah.
Sir, that green line, it is the loss functions were showing no in that graph, that
Uh,
green dots.
yeah, these green dots are where you calculate your physics laws.
Yes, that
So
loss functions.
yeah, so this is where your physics, like I told you, there are two parts to the loss function, right?
Mm,
So the physics loss function is calculated at these points.
yeah. Okay.
This is the, yeah, feedback slash attendance. Okay, hope you guys had learned something from this session. In the next session, we'll be covering a few more interesting algorithms than this one. The gravitational search algorithm there will be more interesting algorithms, as well as uh, giving you guys a flavor of what is quantum computing, like how it is inspired from physics and everything like that. Hope to see you guys there as well. That's it for the session. We'll share the feedback.
Sir,
Uh,
sir,
yeah.
where we can
Don't worry.
where can we get the that feedback form in Google link?
Is this feedback QR code not working?
Not so. So can
Okay.
you give the link? It will be better.
Yeah. Link will be shared in the channel. Time varying gravitational constant. I'm not sure if what I'll share the paper which proposes this time varying gravitational constant. You can look into it probably. Yeah, the feedback form is also sent. So yeah.
Thank you.
Yeah, thank you. Thank you, guys.